Let us now discuss what happens if the reaction is a reversible one. Meaning, so far we have discussed irreversible nature of the reaction, like A plus B going into products. So let us now assume that instead of going into irreversibly into products, let us have we have two components, A and say some product that I'm writing as C. The reason being B actually we are using for reactant. We can also use B, but just be careful that here we're writing the B as the product for the forward reaction, and then B also can get back to A, which means the reaction is reversible. Now, any reaction in principle is reversible in nature, but it depends under what conditions an reversible reaction can become an irreversible reaction. Meaning one of the directions, like the forward direction or the reverse direction, will happen at a much more rate than the other direction. So the reaction will be essentially irreversible. But let us now consider that both the forward and the backward reaction occurs at some appreciable rate, and also let us consider that nu A and nu B are equal, in the sense that it is A and B are interconverting to each other with equal stoichiometry or so, and the associated rate constants are, say, K1 and K minus 1. Some textbook write it as K2, but we are just using the minus notation. So K minus 1 is basically the reverse rate constant for the reverse reaction or the backward reaction. Sometimes we write it as Kf, in the sense it's a forward rate constant or rate constant for the forward reaction, and backward rate constant or rate constant for the backward or reverse reaction, sometimes written as Kb or Kr for the reverse reaction. Now, we have to, before we begin, let us consider what the reaction mixture initially contained. So suppose we mix some A and B together, and then what happens, the A starts converting into B. Now we could also start only from A, and then we suppose heat it up to make some B, and as we are making B, initially of course the concentration of the B will be slow, and so more and more with time more and more A will be consumed and to make B, and then the B concentration will increase, and then they will also further react and then give back A. So sooner or later this initial rate of A going to B will be very high and B going to A will be slow, but sooner or later these two rates will become equal, because you know that rate constant is rate is nothing but rate constant times the concentration. So as the rate constants are fixed with respect to, if the temperature is fixed, rate constants are also fixed. But if you vary the concentration, initially A was at a very high concentration, so the rate of the reaction for A going to B was very high, but rate of the reverse reaction was slow. But as soon as the concentration builds up for B, then the reverse reaction also tries to be significant, and at a point will appear where basically the rate of the forward reaction and the rate of the reverse reaction becomes equal, and that point equilibrium is attained. And once the equilibrium is attained for a particular temperature, if we do not disturb the system, the concentrations will not change, and we know that it is a dynamic equilibrium, meaning it's not like that A is not forming B and B is not forming A. They are interconverting still each other. However, the net amount of A and B is unchanged, and at that equilibrium concentration, we know that at equilibrium rate of forward reaction, which is K1 into A, will be equal to the rate of the reverse reaction, which is K minus 1 into B. And then correspondingly the concentrations, if we write it as equilibrium concentration, we find that this ratio B equilibrium divided by A equilibrium is nothing but K1 by K minus 1. It's a ratio of the rate constant which is also a constant, which we termed as equilibrium constant. Now this equilibrium constant is not exactly the thermodynamic equilibrium constant, in the sense that we just took the ratios of the concentration. If we had written the thermodynamic equilibrium constant, we have to use the activities of the species, and then we have to write activity in terms of concentration, that concentration and with activity coefficient, and then also the concentrations has to be divided by the standard state, so that to make the K equilibrium dimensionless. In this case also it is dimensionless because it's a 1:1 stoichiometry, and the units just cancel out. Now let us try to see how will you write the rate of the reaction. So as before, I can write the rate of the reaction as minus dA dt, but this minus I'm not writing here. Instead I'm writing the minus here, K1 into A. You could have written minus dA dt is plus K1 into A, but I'm just writing it that way. So it is being consumed in the forward reaction, and it is being regained in the reverse reaction. So that's the rate of the reaction. And again we can write it that suppose at t equal to 0 we have, say, A0, the initial concentration of A, and initial concentration of B suppose was B0, and at some arbitrary time suppose the advancement is, say, some xi, and then we'll have A0 minus xi, and here we'll have B0 plus xi. So now you can see if I just eliminate the xi, so this is nothing but A at any time, and this is nothing but B at any time. And so if we just eliminate the xi or equate the expression for the xi with respect to A and with respect to B, we will find that at any point A0 minus A will be nothing but negative of B0 minus B. That will always follow because we just wrote it for any arbitrary time. Now it follows that which means the B can be expressed in terms of A, and that is A0, so this is B, as you can see, plus we'll have B0 because that has a negative sign, and that we are going taking into left hand side, minus A. Now this expression you can put it back here to get an expression of the rate, because since we wrote the rate in terms of dA dt, so we have to eliminate B and write B in terms of A. So we write it like this, minus K1 into A plus K minus 1, and instead of A we are writing as A0 plus B0 minus A. I could rearrange it. So we'll have something like K minus 1. I'm writing the constant terms first into A0 plus B0, and then the A dependent term, which are nothing but minus K1. So this minus K1, and here I have plus K minus 1, but there is a minus in also, so it will be K1 by plus K minus 1 into A. So that is the expression for dA dt. Now we can proceed with that because we have some constant minus something into A, and on my left hand side have just dA dt. I can readily integrate it, but before we integrate that we can also simplify it. And we know that at equilibrium, what happens? At equilibrium, we know that let us just turn the page because we need some space here. So we know that at equilibrium, the forward and reverse rate are equal. So if I plot the dA dt, or if I just ask the question what is dA dt or dB dt, each of them will be 0. So dA dt will be 0, which will be nothing but the constants term, which is this term, minus this term, but instead of A, we'll write A equilibrium, which is the equilibrium concentration of A. So we get that minus, sorry, not minus, it will be K1 times A0 plus B0 minus K1 plus K minus 1 into A equilibrium, because it is the equilibrium concentration. So this term, this constant term, is nothing but, we can just see from here directly, is this. So we can just rewrite the equation for dA dt. dA dt was, first term was this constant term, but instead of that constant term I will write it as K1 plus K minus 1. And the second term, remember, was K1 plus K minus 1 into A. So together we can write it as A equilibrium minus A. So that's a much simpler version of this rate. And then what we can write is, we can now integrate it. So dA divided by, I'm just writing it as A minus A equilibrium, and with a negative sign here, K1 plus K minus 1 into dt, and we can again integrate that at time equal to 0, we have the initial concentration as A0, and time equal to 3, you have A. So that integration is nothing but a logarithmic integration. So we'll have ln. So this integration will be ln, we can actually write it directly between the limits A and A0. So it will be A minus A equilibrium divided by A0 minus A equilibrium, which is nothing but minus K1 plus K minus 1 into T, and we can write it in the exponential form, which is A minus, sorry, this is A equilibrium. A minus A equilibrium is nothing but A0 minus A equilibrium into e to the power minus K1 plus K minus 1 into T. So then we can actually plot it like this. Suppose we have, with respect to time, we are plotting the A0 minus A equilibrium, or you can plot A by A0. We can actually plot A by A0 also. So the A by A0 will be nothing but, if we just follow here, that we'll have, if I just divide both sides by A0, so we'll have A by A0 will be nothing but A equilibrium by A0 plus 1 minus A equilibrium by A0 into e to the power minus K1 plus K minus 1 into T. Something like that we can easily figure out. Now when time is equal to 0, so this term is equal to 1, and then we also see that that time is equal to A0 itself. So A by A0 will be nothing but equal to 1, and with respect to time it will just fall. Now when time is equal to infinity, so then you can easily see that this term actually will be 0 that time, in the exponential term, very long time, and so the concentration we'll get is nothing but A by A0 will be A equilibrium by A0. So that A equilibrium by A0, since everything is scaled with respect to A0, will have some value. So it will exponentially decay and reach some value which is the equilibrium value of is 0, this will be nothing but A equilibrium by A0. So this is the long time behavior. And similarly, the B concentration will increase. Now, initially, if you think that the B concentration was 0, so it will start from 0, although we did not take B to be 0, but we can always put B0 to be 0, and then that will increase, and that will also reach an equilibrium value for B. So which will be nothing but the B equilibrium, but we are scaling everything with respect to A0, so it will be B equilibrium by A0. Now suppose that we know that the equilibrium concentrations will be given by the ratio of the rate constants, and suppose we take a ratio that K2 is say twice of K1, which means at equilibrium the ratio of B is to 1, or B equilibrium divided by equilibrium will be 2, or B equilibrium by A0 divided by equilibrium by A0 will also be equal to 2. So you can think that this is a normalized plot because everything is normalized with respect to A0. So the initial concentration was 1, which is totally, we started with A only, and then so basically at time 0, the way we have written it, A is nothing but A0, and B is nothing but 0, and at time is equilibrium, which means when in a very very long time, so this A has attained the equilibrium concentration, and B has also attained the equilibrium concentration, and their ratio is 2. B equilibrium by equilibrium is 2, but we are plotting not exactly A, we are plotting A by A0, and everything divided by A0, but that doesn't matter because the ratio will still be the same because A0 is just a constant. So you can think that if it is 2:1, then this value will be nothing but 0.33, about 0.33, and this value will be nothing but about say 0.66 or so, because if we add at any time A equilibrium plus B equilibrium, you can see the mass balance here that we wrote earlier, that at any point this should hold. So initial concentration of B0 we took to be 0, so at any point, if say at equilibrium point, so this B equilibrium plus A equilibrium will be a 0. So we see that if we have 0.33 and 0.66, then the ratio 2 is also maintained, and 0.33 plus 0.66 is 0.99, which is roughly equal to 1. So that way the curves will look like. But it might have an opposite situation, meaning A can be also higher in proportion, but that will be set by the equilibrium constant, which is a function of temperature alone. So as long as we are not changing the temperature of the system, the equilibrium constant is kept constant, and we'll see the similar ratios for A and B, which is given by the dictated by the temperature. So the system has a system of A and B have now attained equilibrium in the very very long time limit, and the time concept is also interesting here, as we just discussed, because it will happen only at the long time. The reason being, you can easily figure out that only at long time, initially only the A was forming into B, and then slowly as the B concentration increases, the rate of the reverse reaction also increases, and then at some point they match, and once they start matching, then there will be no change because it has reached a equilibrium point, which is according to this plot is happening say somewhere here. So after this time, basically the slopes have become 0. So as you see, the slope, initial slope was very high here, but the slope of the dA/dt curve is changing, and the dB/dt curve was also rising, and that is also changing. So then after equilibrium has attained, the slopes are 0. So basically there is no change, and that's exactly what we used in this condition, that at equilibrium we made it to be 0, and that's how we established this condition. Now let us think about another interesting situation where we have some species A is going into B, but it can also go to another species which is C, and these are called competing reactions because there are two competing pathways where A can go into B, A can go into C, so it is called competing reaction. And of course this is first order, in the sense that we are assuming that the reaction A to B is first order with some rate constant K1, and A to C is also first order with some rate constant K2. Now you can easily figure out what is the kinetics or the integrated rate law with respect to A. That we can write as minus di dt. Remember that nu A is 1 in this case, so the stoichiometry we are taking just 1:1. The di dt is nothing but minus K1 into A for this path where A is forming the B, minus K2 into A where the other path where basically A is forming C. So it is nothing but minus K1 plus K2 into A. Now you can easily integrate it out. It's a first order rate equation. So A is nothing but A0, where A0 is the initial concentration of A, times e to the power minus K1 plus K2 into T. Now we can plot it, but before we plot it, let us see what is the concentration, how the concentration of B and C varies. Now dB dt will be nothing but K1 into A, because that is formed from A with a rate constant which is K1, and A we just solved. A is nothing but A0 into e to the power minus K1 plus K2 into T. So you can easily integrate it. So dB will be nothing but so this is integration with respect to that. Okay, yeah, so we can write it like this. dB is nothing but K1 into A0. Remember A0 is a constant, into e to the power minus K1 plus K2 into T dt, and we can assume that at time 0 the initial concentration of B was 0, and at some time arbitrary time t, initial concentration of B was just B. So my left hand side integration will be just B, and right hand side, so it's integration of e to the power mx dx. So that is nothing but e to the power mx divided by m. Here m is minus K1 plus K2, so you can just write it K1 divided by minus K1 plus K2, and this will be into e to the power minus K1 plus K2 into T, evaluated between the limits 0 and T, and that limit, if you see at 0, it is e to the power 0 is 1, and that is the lower limit, and the upper limit will be just e to the power minus K1 plus K2 into T. So it is e to the power minus K1 plus K2 into T minus 1, but that minus 1 we can actually introduce the minus sign inside and write it like K1 plus K2 into, we are writing the lower limit first, e to the power minus K1 plus K2 into T, and this is the concentration of B. Similarly, for the concentration of C, you can easily figure out that C will be nothing, the rate equation, instead of if we write C here, the K1 will be just replaced by K2. So this will be nothing but K2 into K1 plus K2 into 1 minus e to the power minus K1 plus K2 into T. So if you now plot the three terms which are A, B and C in the same plot, you can see that if I start with say A, and again suppose I'm plotting by A0 or something like that, So that will start from 1 because I have normalized it as a function of time. So I'll have a very steep drop. Why steep? Because the steepness is because it is an exponential decay, but the exponential constant is nothing but k1 plus k2. It's a k1 plus k2 means actually it is a joint contribution of k1 plus k2 because A is decomposing into A as well as into B. So it has two pathways. However, when the B rises, B will rise at a rate which is k1t. You can easily see the equation of B. So it is 1 minus exponential minus, which is basically exponential growth. So in the very long limit, you can always see that in the very short limit, when t was equal to 0, so you will have basically 1 minus 1, which is 0. So for C also it is 0. So the initial concentration we took to be 0, because all the initial concentration we suppose that it is only A0. And remember that the initial concentration of B was 0, and similar argument we also provided for initial concentration of C, and which means they will both start from here. But as time progresses, you can think that at a very, very large limit, this when t goes to infinity, so this term goes to 0, both these terms. So I'll just have 1. So I'll just have B concentration to be K1 divided by K1 plus K2, and C concentration as K2 divided by K1 plus K2. So they are going to be a constant in the asymptotic time limit when the time is very large. When the entire A has decayed, let me just draw the A curve once again. So it will be, if I want to show it, it will be much more steeper. So it decays much earlier, and then this B actually gets converted to, sorry, A gets converted into B, and A also gets converted into C. So let me just draw it once again. So this was the axis, and I'm plotting here A by A0, or B by B0, or C by C0, everything, the concentration versus C0. And then the concentration for C, suppose, is here. And we can easily argue that, just like the earlier case, that if K2 is like twice K1, then you see that the concentration of B will be just twice the concentration of C. And if we are plotting something like this is a plot of, say, B by A0, we're normalizing everything with respect to A0. So this is, say, C by A0, and this plot is, say, for A by A0. So then, as before, we can argue that this will reach something like 0.33 because it's a normalized curve. This was 1, and this B, sorry, concentration of C will reach 0.66. So their ratio is just like 2:1, and the ratio is dictated by the ratio of K1 and K2, because as we just said that at t equal to infinity, or t tends to infinity, the ratio of B by C will be nothing but K1 by K2, or C by B will be K2 by K1 when t tends to infinity. So that ratio is now maintained. So this is not an reversible reaction, remember. However, this is an irreversible reaction because A is completely decaying and to 0 actually in the long time limit, and B and C are formed, but B and C are formed, and then the final concentration of B and C are maintaining a ratio, and that ratio is maintained by the ratio of their rate constant. So this kind of situation is known as kinetically controlled, in the sense that the kinetics is controlling everything. Now, when we discuss the Arrhenius rate equation, how the rate constant depends on the relative rates, or how the relative rates actually control the products. Here actually it's a very interesting situation, but when we discuss the Arrhenius concept, that if I vary the temperature, how the rate constant changes, and there we can see that there is also another way of thinking of the products, that the relative stability of the products might be very different. in the sense that B can be actually more stable than C here. So in the long time limit, we'll see that the situation might get reversed. So that we'll discuss when we have a very some elementary concept of activation energy. So for the time being, here it is a concept what we just developed. So here C is known as kinetically controlled product. Or the reaction, it is better to call that this reaction is actually kinetically controlled, means actually the rate constant of that species will be high in the long time limit, or the concentration of that particular species will be higher in that long time limit, which had formed at a faster rate, because all the ratios are now given by K1, K2, which are actually rate constants. So the initial rates of the reactions, or the rate constants, are actually dictating the final distribution of the product, and that's why it is called the kinetics is basically governing everything. There is also another thing called thermodynamical control product, and we'll also see how these two are interrelated and how we can actually plot it in a free energy diagram, but that we'll discuss when we discuss the Arrhenius equation. And such kind of reactions which we just described are called as kinetically controlled reactions. For the reaction to be thermodynamically controlled, we have to have two equilibrium established between them. So there will be a reverse reaction also, which is K-1, and there will be another reverse reaction K-2. So K-1 is the rate at which B is forming A, and K-2 is the rate at which C is forming A. So under this condition, we'll see that C and B can also come back to A, and then A necessarily will not go to 0. Actually, A will never go to 0 because there is equilibrium. And then you can see that if these two are in equilibrium and these two are also in equilibrium, then you can actually show that B and C are also in equilibrium. It is through A. So B cannot directly interconvert, B and C cannot directly interconvert. So B can convert to A and to C, and similarly C can convert to A and to B, but which means they are interconvertible. And but then we can show very nicely that we can actually control the ratio of B by C by temperature also. And in a very interesting case, we can show that in the very long time limit, this curve may actually get reversed, in the sense that in a very early limit, when the kinetics actually controls everything, now C will dominate B, but then at a later time, then we'll see that B actually dominates the C. So their curves actually switches, and how temperature can be an effective parameter in that switch we can we'll discuss at that point. So in the following section, which we are going to discuss in the next section, we'll consider another interesting kind of reactions, which are known as consecutive reaction. And then we'll end our first part, which is basically the reaction kinetics. So we consider different models, and then that will be our last particular model or last example, where we have some reactions happening in a consecutive fashions, and how to get an integrated rate law for the consecutive reaction. That we'll discuss in the next section.